Okay guys, so now let us work on this example. In your notes we have a 3/4 of an inch 16 UNF, basically fine pitch. 3/4 of an inch is the major diameter of the bolt, and it has 16 teeth per inch, and then the length of the bolt is 2.5 inches. SAE grade 5 bolt, so this will tell you what the strength of the bolt, right? It will tell you the proof strength of the bolt, the yield strength of the bolt, and is subjected to a load P equal to 6,000 pounds in a tension joint. The initial bolt tension is, so this is a preload, 25,000 pounds, and the bolt and joint stiffness is KB is equal to 6.5 megapounds per inch, KM is equal to 13.8 megapounds per inch. We need to determine the preload and service load stresses, compare and the stresses to the proof strength, specify the torque necessary to develop the preload. Alright, so we said already the force in the bolt, right, is going to be equal to C multiplied by the external load applied on the bolt plus Fi, right? So the bolt, if there is no preload on the bolt, then the load inside the bolt is simply Cp, right? And if there was no external load applied on the bolt, there is only the preload, right? Okay, so the first part of this problem, we need to find the preload and service load stresses. So the preload stress is basically going to be this associated with the preload. So preload stress is equal to Fi divided by At. At basically is the tensile area of the bolt. As we said, the bolt basically will have a portion of it which is not threaded, and then there is the portion of the bolt which is not threaded, right? You can get that AT is the area of this threaded portion, and then AD is the area of that non-threaded portion. When you are calculating the preload stress, you are calculating the stress based on the weakest or smallest area, which is going to be this guy. Okay, so the preload stress is going to be this. The service load stress, which is basically the actual stress, which is going to be equal to FB divided by AT, right? CP plus, and now we can make the preload stress over here, AT. Alright guys, so it's pretty basic. How do you get AT? You get it from the table, right? You get it from the table based on this information. So 3/4, this is the size of the bolt, and then this comes either as 16 or I believe 32. We're gonna look it up in a second. Compare the stresses to the proof strength. So the proof strength of the bolt, you get this guy from what grade the bolt is, right? So the grade of the bolt will dictate what is the proof strength of the bolt, and you evaluate this stress based on that. Specify the torque necessary to develop the preload. So if you remember, this basically relates to the power screws, right? So you have a torque and then you have a preload, right? So this is it. So basically you sort of like relate the rotational torque that you need to apply on the bolt to rotate it to develop that preload. Okay guys, so this is really all that you have to do here, and let us actually look at the solutions for this. Alright, so here is the solution that we have. So the preload stress, like I mentioned, is sigma I is equal to Fi over At. How do you get At? You get At from that table, right? So the bolt was 3/4, right? So 3/4 is right here. So 3/4, which is basically 0.7500. This is a major diameter of this, that would be AD. Now you need to find AT. So there are two values for AT. One value for AT comes for a 3/4 of an inch that has 10 teeth per inch. That would be the coarse pitch, and there is another version for that bolt that has 16 teeth per inch, which is in our example. And AT for this one is actually equal to how much? It is actually equal to 0.373. So remember, so you basically your major diameter of the bolt is 0.75, but actually the tensile strength area is actually much smaller than what you would think. It is 0.373. It's almost half that. So you see the thread basically is going to be deep down into it, right? So this is your bolt, right? This is 3/4, right? But when it actually comes over to the thread actually looks like that, sort of, right? So this area right there is AT. Okay, AT is the area that is being used. It's actually somewhere in the middle. This would be the minor. So AT is the average area that would correspond to that thread, and that average area in this case is here. Okay, very good. So this is your sigma I is going to be equal to 25,000 pounds, which is the preload force, divided by this area 0.373, which is your AT. Then you can find your preload stress. Service load is going to be FB over AT, CP plus FI, which is what we discussed. It's going to be equal to this. You need to find C, right, the joint stiffness. In this problem, basically, they provided your KB and then KM here, right? KB is actually equal to 6.5, and then Km is equal to 13.8. So you just need to find your joint constant. KB divided by KB plus Km, it would be equal to 0.330. So that number C simply means that the portion of the load P that actually goes into the bolt is going to be 0.330 multiplied by the load. Alright. Getting the stress is simply you apply AT again, and then sigma I is already calculated, 67. So this would be your the service load stress. So that would be the stress that develops in the bolt as a result of this preload that we have. So remember, the more preload that you apply on the bolt, then the higher the stress is. So sometimes you might even break the bolt simply by tightening the nut a lot. Alright, so if we were to compare that as a proof strength, so let's actually look into our the grades of the bolt. And this is gonna be my table, right? This is all in your notes, guys. Okay, so the grade of the bolt in this case is what was the grade? The grade of the bolt in this problem was equal to how much? Yeah, that was SAE grade 5 bolt, right? So grade 5 bolt, you need to look up in your grade sheet, right? So grade 5 bolt, those who have a diameter between quarter and 1, and here we're not looking at AT, we're looking at the actual nominal diameter. Between quarter and 1, basically, your minimum proof strength is going to be equal to 85 KSI. Minimum tensile strength is 120, and then minimum yield strength is equal to 82. So this is a yield, this is a tensile, and this is a proof strength. So we are going to be looking at the proof strength when we evaluate bolts. So in that case, it's going to be equal to how much? 85, right? Which is here, right? Minimum proof strength is equal to 85 KSI, and then here basically you can compare them. In this case, it says service load is 15% larger than the proof strength. Smaller than the proof strength, right? So 72.15. Or you can find this as a safety factor. Now, the torque that is needed to develop the preload, if you remember from our power screw equation, we actually had this equation where you directly get, so that would be the torque, and Fi is your preload, D is the diameter, and then K is the torque factor, which you can look up from table 815. So we actually had that equation for before. Or you can simply apply the raising torque of a power screw, where you can find the torque needed to raise the torque basically applied on the nut that need to develop this preload or this axial load that develops in the bolt. So in that case, it is simply 0.2 multiplied by F, 25,000. This is the preload times 0.75. So this number is the amount of torque that you need to provide to the nut in order to develop this preload. Alright guys, so that really sums up this example. So what you need to be able to find is you need to find the preload stress, which is related directly to the preload force, and the tensile area of the bolt. You find the tensile area of the bolt based on the bolt size designation and the number of threads. Basically, you can find AT. From there you can find the preload stress, and then if I tell you find the service stress, you basically have to add CP. So CP plus FI divided by AT. CP plus FI is total force in the bolt, AT is tensile area. You can find the service stress, and then what you need to do sometimes is you need to find the torque that is needed to torque that nut, and you can find it based on this equation or based on the power screw equation, and that would give you the same number. And that would be it for this problem. Okay guys, so now we are going to look into the safety factor of bolts. Bolts have two safety factors. The first safety factor is going to be based on the proof strength, so it will actually be equal to so this is how we're going to actually develop that safety factor. If you remember in our lectures, we said the safety factor is related to a force, right? And if you look at the total stress inside the bolt is going to be equal to Cp divided by NAT, where N is a number of bolts. So the more number of bolts that you have, you are going to have, you will basically reduce that force P. So that force P is going to be distributed over that many bolts, plus Fi divided by AT. So the preload is the same on every bolt, but the total force will be distributed on all the bolts. That is why we are dividing only this P by N, and we're not dividing the preload force by N. Alright, so the total force or the total stress in a bolt is going to be equal to Cp NAT plus Fi divided by AT. And the safety factor, the first safety factor of a bolted joint is going to be called the load factor, which is N. And basically, when I put the safety factor, I'm going to put the safety factor directly in terms of, in front of P, right? So by how many times I can increase that force P in order for me to reach that proof strength of the bolt, which I'm going to look up from that table based on the grade of the bolt. Alright, so now if you solve for N, you are going to end up with that relationship. So N is a load factor, right? And then this is basically a safety factor of the bolt. And that safety factor, if that safety factor is 1, it means that you are exactly at the proof strength. If that number is 2, it means that for the same preload, you can increase that load P by 2, and then you would be at the proof stress. All right, guys. So this is the load factor, and this is one of the safety factors that is used in bolts. And if N is greater than 1, then the bolt stress is less than the proof. If N is greater than 1, yes, the bolt stress is less than the proof stress, meaning that you can increase P by that value. All right, so again, the safety factor here only applies to P. It doesn't apply to the preload. Why? Because the preload basically applies to every bolt. Basically have that same preload, right? We're not multiplying the preload by the safety factor. All right, guys, so the other type of safety factor for bolts is going to be called joint separations. All right, and before we actually look into that, I mentioned something regarding the preload. How do you get the preload of a bolt? The way to get the preload of a bolt is using two ways. The first type is you calculate the preload based on reused connections. So if you actually have to replace the connection, then your preload would be equal to 0.75 AT, which you know from the table based on the bolt grade designation number, and the proof strength, which is based on the bolt grade. So for a given bolt, if that bolt is to be removed, reused in a different connection later on, then you would only make the preload to be equal to 0.75 multiplied by 80 times SP. But if that bolt is to be permanent, then your preload has to be equal to 0.9 80 times SP. And then you have this guy, SP is, like I said, proof strength from the grade of the bolt, and then 80 is from your tensile area of the bolt based on its geometry and based on its designation. Regarding the joint separation factor, it's going to be equal to this. So if you guys remember the way the bolt is done, right? So this is your bolt, and then this is one member, and this is the other member, and this is a nut, and then here we have the load P. So remember when we solved for Fm, right? And then we said Fm was equal to 1 minus C, P minus Fi, right? So that would be the force inside the member. The joint separation occurs when the force inside the member is 0. So if the total force so remember, the bolt is trying to apply compression, and that external force trying to open them up, right? And when basically that force minus the preload is actually equal to 0, it means that this gap here, that we're going to actually we won't actually have any compression between those two plates, and the coefficient of friction, the frictional force between them will basically be 0, and then now basically you risk to shear the bolt, right? So this is called joint separation number. So you want to make sure that you're not separating the two joints at all. So by setting Fm to be equal to 0, and multiplying P0 by n. Here, if you put n in front of P0 and then you solve for n, basically you are going to end up with n is going to be equal to what? Fi divided by P minus 1 over 1 minus over C, right? So again, safety factor of joint separation is going to be proportional to the force. So you're going to basically put that n over here and 0 in front of this, and then you solve for it, you are going to end up with that number. So this is the safety factor for joint separation. Again, long story short, guys, we have two safety factors for bolted joint. The first safety factor is the load factor, which has to do with the proof strength, by how much you can increase that load for you to basically exceed that proof strength inside the bolt. And the other safety factor is based on the joint separation, which is when the force between those two plates becomes 0, and therefore basically the friction is lost between them, and then basically this plate will slide toward the right, and then this plate may slide toward the left, and here you shear the bolt, and then this is another issue. So this is going to be that safety factor.